Welcome back. Just had a small rant here. So yeah, so we've touched on I'm gonna just where is this is what we did now. Just copy this thing so that I remind myself to make a note. And so now we're heading for the series arrangement now. So let's see. Sorry, we're heading for the parallel. So we've completed the series. So let's see where we can go. So yeah, I just want to actually get that note down, and then obviously keeping in mind we can actually do parallel. Obviously, we have some experience with what a parallel member is, and it's a member within a member. So I would say, but um, what's interesting to note here is that for temperature stations, we still experience the same force, but so F1 still equals F2. However, what changes is our changes in length. We don't actually add them up, yet we subtract. So just talking to that now. So if you look at the figure on the right over there, let me just really just isolate this so that we can actually get a good feel for it. I'm just gonna make this nice and big because you can see, yeah, something like this. Now what's very interesting with the parallel arrangements now is that the sensors, when it contracts or expands, when it's fixed, it won't be the same. We'll have different sensors now. So in the first situation, the original temperature, as you know, if it stays constant, then no stress is induced. If you're allowed to freely expand, exactly the same. But what's important to note now, when it freely expands, what happens? You're going to find the material with a higher coefficient of expansion to increase faster than the one which is not. So that's why if you look at the second situation, you see, let's say there is copper in the middle and steel, a steel tube with a copper tube, a steel tube with a copper rod, a shaft inserted inside. And now when we obviously clamp it on the one side and when we fix it, what's going to happen now is that we're going to end up finding that the copper is going to be compressed, where the tensile, where the steel will be in tension. Do we all get this concept? This is very important. I'd like to have a discussion on this one, a small discussion. Do we all understand that? So material one is copper, material two is steel. One expands faster than the other one, but if it's fixed, you're going to find out that the copper, which is in the middle, is going to be compressed, whereas the steel will be in tension. This is full. Do you maybe want to touch on that? Who is Mr. Kiefer? His mic is on here. Students, are we all there? You all get this. We don't want to be coming back and figuring this out. Oh, Mr. Mantam is also here. Can you guys hear me? First of all.
Yeah, we can hear you.
Okay, thanks. Okay, yes. So, in keeping with that knowledge, back to the equations which you talked about, and here they're saying from 7.3, it's clear that material one will be compressed. That's against the wall where the steel will be in tension. I really like these questions. It normally comes up. Well, the three main types you've seen now, or the third one you'll see. I like them because they really, especially this one, it really emphasizes like when you have two different types of loading, and you'll see. So once again, you have a statics equation and a compatibility equation. These equations are in the formula sheet, if I'm correct. Just have a look. I did post some formula sheets this weekend. Yeah. So we are working on the formula sheets. There are formulas which needs to be added. We will talk about that. But I'm not really worried about strengths. I'm more worried about I'm just sort out electrodes one and then mom specifically as well. Nevertheless, so these are the models we use. All right, guys. So we're gonna solve this example. And then yeah, we're gonna. I was thinking of the. I think we won't have enough time, so we'll probably have to do the other one. And then yeah, we're basically done for temperature stresses. All right, so let's just quickly copy this guy. The guys, please, this is, I mean, strengths is, like I said, I'd say it's the easiest, and then thermos, and then electrodes, and maybe mom would be the most challenging, but it depends on your tastes. So I don't want people to really, really, hey, what's going on here? But please, if you don't understand something, it's good to always just ask. Try to clarify as much as possible. Okay, so what we have is a steel rod. Let's go find our sketch. We used to work on a sketch. Got a steel rod and a copper tube, if I'm correct. Nice. And what happens is, yeah, of course they give the dimensions, but let's see what's important. So they basically, if the rod and the tube are rigidly fixed or fastened together at the end, at each end, they're fixed essentially, and the temperature increases by 250 degrees. So a big increase. What is the magnitude and the nature of induced stresses? Now this is just fun. Now part B, what we're gonna do, we will introduce a compressive load. That's what I'm talking about. So now we actually applying another load. We could have maybe even applied bending on the whole assembly, you know. So this is I like this one because it has different types of loading induced. Okay, so obviously because the forces are the same, we can start doing that. So let's quickly just get that down, getting our ratios in. This is an example in textbook. Yes, it is. So and also what we expect is that you're looking at the sketch is that because your copper has a higher coefficient of thermal expansion, as you can see there, that's most probably going to be compressed, whereas a steel will be in tension. So this is where it gets. So it works differently when we parallel. So it's a whole other set, a whole other case thought to think about. Okay, just go A. So here we're gonna go F copper equals F steel, and then this should be stress area copper, stress area steel, and stress of copper. We can just quickly stress of steel. We can say area of steel divided by area of copper, and we'll get 0.3789 steel. So I'm assuming we're all happy with this. This is standard. So we're first looking at the temperature increase now, right? And then let's have a look now. So remember our next equation, our compatibility equation, will change the length equation. In this case, it looks like this. Because are the lengths the same here? I'm not sure. Stress LB. She's going to be steel. So we're probably going to end up with two equations to unknowns again. Stress in copper. And that'll be equal to you could say L1 alpha 1 minus L2 alpha 2, or steel and copper. That's temperature here. But let me just make sure. Are the lengths the same as the students? Yeah, they're both 1 meter long. So then if the lengths are all the same, we can just simply have this. Instead of wasting time, we just forward this one. And it'll be alpha 1 minus alpha 2. And the temperature change. All right, so let's see. So let's just equate these bad boys and see what we get. So can someone just give me this this value here? I'll just leave it a good space on that end and then a decent space on that end. And of course here we could have coefficient of thermal expansions. So normally here I normally always just keep the highest minus the lowest, just so that it become positive over here. So in this case, the higher coefficient would be 20. So I opt for this to be always positive. So I actually just rearrange it, and this will be 12. Yeah, that's what I always do. So I'm just making aware of that, and that's around this 250. Okay, can someone just give me these coefficients here, and of course what that is equal to. So always try to keep this positive. You don't have to. Of course you can play around with it and stuff, but yeah. Let's see. If you make it negative, then the senses will probably all work out and stuff. But yeah, you can do that as well. And we can actually keep it negative, and then you actually see it all work out the same way. So can I get those coefficients, please? There is no one here today.
The stress of the steel is 95 over 36, the stress of the copper.
90. Can you just say it again?
95
sure, I'm
over 36.
I'm talking about the ratio. I'm talking about the is it like I'm at the second equation over here. I don't know what you're exactly referring to. You're talking the ratio between copper and steel.
Oh, you're on B already. Sorry, I was busy with something else there.
Yeah, I thought, yeah. So, sounding a bit, I don't know, it's my speaker. So I'm talking about that there. And then your steel's elastic modulus, so that'll be 1 over 200. So this will be 5 times 10 to the negative 12. And this will be over here. Copper's elastic modulus is 1 over 100. Which is 10 times 10 to the negative 12. Yeah. Okay. Are we all happy with this here, students? You guys are awfully quiet. Okay. So we can just score that in our matrix if you want. If you're into that. And we're going steel copper. So I think we should rearrange this. Oh no, we don't have to. So we can just say steel 0.3798 minus that equals 0. Okay, so 0.3789 minus 1, 5 times 10 to the power negative 12, and then this is that was that a 14 or 10? I think it was 10. Stress of steel, sorry, stress of copper, and this was 0, and this is 2 times 10 to the negative 3. Okay. Students, do you agree with these answers? Where are you guys? Who's here? Loazi, are you here? Mr. Doyle? Are you guys lost?
I'm trying to keep up, sir.
Okay. Am I moving too fast? Lost. Why are you lost, Mr. Abreu? What's wrong? You shouldn't be lost here.
So I would like to understand the question better before going to attempt straight. I would like to just read the question carefully, please.
Okay, it's in your textbook. But what I'm telling you is that I moved too fast over this thing. That we've got a steel rod placed inside a copper tube, right? And then we increase the temperature to 250 degrees. What happens then is that due to the coefficient of thermal expansion, one will extend faster than the other one, right? So obviously, because they're fixed, the hole will push the copper tube, right? Therefore, it will induce a compressive stress, whereas on the steel counterpart, as it's fixed, it will increase. Yeah, you can use a textbook method. It's no problem. It makes no difference really, honestly. So what are the stresses in steel? So Mr. Abreu, I hope you understand. So remember, series is this, and now we have parallel members, right?
Right, I get it, right.
Yeah, and that's all what's happening. And now we're just seeing, and I want to touch on, we could have kept this negative and you would have gotten the senses right. So you can use a textbook method. I think this matrices are confusing some people for some reason, but it shouldn't be. So your first stress should be 227.56 MPa. So the calculator doesn't tell you the answer, and this will be 86, I think. Yep, 86.21 MPa. Just make a line here. Now, what I'm saying is that if you swap this two around, this over here, if you had it stress steel minus that, this would have been a negative here, right? And if you did that in a calculator now, I mean, just in a matrix, you just say minus 2 times 10 to the power negative 3. What you've gotten is that this answer, that have all been negatives actually, funny enough, which is quite strange. I expect them to work out correctly. So yeah. Is it true to all that? It should make sense.
Sorry.
Okay.
Sorry,
Yeah.
sir. Could I ask you to do the? Could I ask you to show us how to do the matrices again? I'm sorry.
Like in the calculator or?
Yeah, in the calculator.
Yeah. Okay. I mean, guys, if guys are like really just like worried about this method, all you all know that you just have to substitute this guy, right? This into that equation. That's all it is, right? I'm just letting people know. That's all what you're doing. You can do that. That's perfectly fine. You don't have to do the matrix method. I'm just showing you, but I'm concerned of, are you guys understand the principles of like when something's in parallel? That's what I'm really concerned about, not really the method. But I guess that bothers people. Does it feel like something new? But I mean, I know for the guys who are here last semester, it shouldn't be a problem. Let's just quickly see. Share this calculator now. All right, so share. Yes, Sasha, go for it.
So can I just make a quick suggestion? What I find helpful for me,
Yeah.
your method is very cool if you are very comfortable with all the variables. But if you don't, there's too many components at the same time. I try to eliminate as many variables and have them in terms of each other. So if you work out the stress and the area in terms of stress and area of the dissimilar materials, then you're eliminating one variable, if you get what I'm trying to say. So then if you're changing, like applying it like that worked a lot better for me than having too many variables on the page, because then it gets confusing.
No, I know that. Yeah, it's because you guys are obviously familiar with a certain approach, and I tried to introduce it, but like I said, it's making guys. You don't have to use this calculator method. I can just go substitution. I think I'll just keep it substitution. Guess people are not really a fan of quick. So I'm more about the engineering science and the actual thing. So anyway, the first one is a simple. Oh, what was my calculator? Yeah. So mode equation. The first one, two equations, two unknowns. Again, guys, you can just substitute. I didn't expect you to do this. So it's 3.3789. That's the first variable, right? That's still. Second thing is -1. That's going to be 0. Next one is going to be 5 times 10 to the -12. And the other one's going to be 1. I'm just going with what I typed in here, times 10 to the -11. And of course, that's equal to that 2 times 10 to the -3. And so equal, whoop. I made a mistake. I put it in the wrong place. So that's 1. It's weird. I haven't calculated in my hand and actually just typing as well. So I'm like looking at both of them. Okay, cool. Oh man, I'm missing something here. 0.379. Let me just check my stuff here. It's 7891, 0, 5 times this. Oh, I typed in the wrong place. That's 5 times 10 to the -12. There we go. That should work out. So that's 227, and I think this car was 86.22. So, oh, did you see that? That's what I just did. Don't have to do the students. It's not compulsory. It's not compulsory. So, did you get that? Are you happy?
Happy.
Can you guys hear me? Oh, sorry, man. Yeah, I don't know. It's more Wi-Fi. But so what I'm asking is
Yeah,
for
we
the
got you now,
areas.
bro.
Okay, great. Sorry about that. Yeah. So again, I'm just gonna. The first part of the question, we look at the temperature loading, right? The second part is the mechanical loading. So when we look at the mechanical loading counterpart, you have to remember your previous Tension Materials 2 and look at that static incompatibility equation. So in this case, the change length equal and your forces are the algebraic sum of the total force. So what I'm asking now is just give me the areas of the copper and the steel. And obviously with substitution, you can actually find the individual stresses induced by the 50 kilonewtons. Is that clear to everyone? Are you guys finding this challenging? I haven't heard from Jason or Annalisa or today at all. It's clear. Okay. People sleeping. Okay, so give me those areas, guys. Or is it always in the book? Must I go look in the book? Hi, Annalisa, I see you saying. Are you saying something?
You were just going a bit too fast, sir. But
Oh,
I'm
okay.
okay.
Okay, that's what I thought. Yeah. Thank you for saying something. So, area in copper. Let's look at the area in copper. I'm assuming everyone has got it in textbook. I mean, that's really a bit late now. So copper has. I don't want to spend my time doing like elementary calculations because it takes a lot of time.
Do you want the ratio?
Yeah, no, I have the ratio here. I'm looking for the areas. It's just to plug those in there, really. I mean, so it's the 60 minus 35. Yeah. Looking for this. It's 1.83865. So of course this goes in here. The steel, that's a rod. That's 30 millimeters. And that just goes in here, right? So of course, you guys don't like matrices, so you just can sub in over here, right? And you get your stress in copper and your stress in steel. Give me the magnitude and the sensors. Yeah, sorry man if I'm going too fast here, but yeah, that's the problem. More sugar here. Okay, so I'm waiting for the stresses of the copper and steel. Let me see here. Mr. Neto, Mr. Pereira, Mr. Matoso. Are you guys winning?
Yes, sir. Always winning, sir.
Fantastic. Okay, so now I'm gonna give it to me. Should I? Mr. Matambo, you should be fast now. Yeah, hit me with the stress of copper and steel.
The stress of the steel is 196,0489 megapascals. The stress in the copper is 101.475 megapascals.
Fantastic. Okay. Did everyone get that? Obviously, they should be able to calculate. All right, let's see. You said it's 196, 19, was it 19? What is it? Oh man. Your stress should be in steel 30, 30.5. Whoa. And the stress in steel should be no, it's the other way around, sorry.
I gave you the resultant stresses.
Yes, exactly. Yeah, that's what I'm saying. I realized that now. I didn't just see this like correct, but I realized that. Not sure where everyone else is. 2.25. Right. And because this is also compressive load, guys, these are, there's my red pen. They're all compressive, right? And now, students, this is where the fun part comes. This is what I love the most. When you're working on the resultant stress now, so I'm going to say resultant stress. Steel, we look at the first one due to temperature. So I'll say temperature stress and then the mechanical stress. With respect to signs, I'm just saying we're just adding them up. Lucky they're no vector. You think they're no vectors, but anyway. So it's plus 227.56, they're all at MPa, minus 30.5. Therefore, the resultant stress would be equal to 19227.5. Guys, this is a very important, very, very important part. Like, this is like the megapascals. Resultant for copper is going to be 86. That is negative 86.21, and also negative 15.25. That's the resultant stresses. And we should get 101.46. That's what I get tonight. I'm just using those values. So that resulted in the tensile stress. Oh no, it's doing it again. Yeah, laptop just froze again. Okay. All right, guys, can you guys hear me? I'm back.
Yes, sir, we can.
Okay, is everyone happy with finding the resultant stresses? Thank you. Is everyone happy with finding the resultant stresses? Is there any questions? Please ask now. Any questions with finding the resultant stresses? Is everyone happy? Do we understand there's a thermal counterpart and then there is a mechanical counterpart, right? But you're not done in the question yet. Let me just check. Mr. Mbambisa, are you and Mr. Mutaung, you guys get this concept? Ms. Jack? I'm sure Mr. Kassa, are you good? Mr. Bason?
Yeah, yes, sir.
Okay, fantastic, right? Okay. So normally standard, they're gonna ask you to find the overall change in length. Thank you very much, right? And the overall change in length, once again, we can do it for steel or copper. And in your book, they started off with copper. So I'll show you how to do steel, right? So consider steel. Let's talk about this, right? So the first thing you have to do, it's a similar thing where you assume that it expands freely. But then I'm going to show you guys a fantastic, not a shortcut, but I've kind of figured out over time. So you first consider thermal expansion, and that's going to be 1 meter times 12 times 10 to negative 6 times the temperature increase of 250. All right. Now we have to consider all the temperature loading basically due to the thermal loading and the mechanical loading. So obviously, what we really just do, we say stress LE, right? I'm gonna call it thermal. Obviously, we know we're dealing with steel, and then we also have stress LE, the mechanical counterpart. But of course, we're looking at the steel. The thermal counterpart gave us a tensile force, and of course, the compressive load gave us a negative, that 50 kilonewton induces a negative stress. If you actually look at this properly, this stress was given as 227.557, and this stress was given as at 30, right? 30.5, right? So the length and the elastic modulus is basically the same for this material. And what this actually is, this is just the resultant stress if you add those two together, right? The plus 227 minus the 30. So a quick shortcut basically is just to do this times 250. Look at the resultant. The resultant was a positive 197.06. Times by the length. The length was a meter as well. And of course, your elastic modulus remains constant. So what I'm saying is that once you find a resultant stress, it's just a matter of taking that, making sure you take the right sense, and then bam, Bob's your uncle. Quick. So can someone just compute this change in length for me? This will be the total change in length, by the way. We're expecting to get the exact same answer in the book, which is around 4 mil. So Prof. Engelbrecht, can you please confirm there for us?
3,9854 millimeters.
Is it the same? You check it out.
Yep.
Yeah, fantastic. Never trust me, eh? Let's check. So we get roughly the same answer, right? What's a point? 0.001 mole between friends. No one's gonna die. Okay, so you have the answer for copper as well in your book. You guys still ready for more? We've got some time left. Well, we've got 10 minutes left, I think. You guys have enough for today? Oh, let me open that so long as well. Let me. I guess no one's. This is Monday or what? What happened the weekend?
So can you try do the last question? 7 point. What's it now? 12, something like that.
Moses. 7.12. Sure I can. What is it? It's a rim.
Yeah.
Yeah. Yeah, you see the things like those certain problems I don't really want you to waste your time on, man. Like those are like, yeah, it's
7.12 I couldn't solve either. I didn't grasp the concept. There was another rim that was earlier on that was quite easy, but this rim one I don't get.
Yeah, so I think I'll make you aware that it's like certain of these, like these other problems, like these, like the bolts and stuff is fine, but those ones at the end, man, which the context is a bit. I don't really care about those problems, honestly. You know, I'll post what you need to follow. Like I'll show you now exactly what I'm talking about. If you guys can go over, I think I posted this thing here. So some extra problems here. Yeah, this is the one. Yeah, here's some good extra problems, and I'll post maybe 2 or 3 more extra ones. Go over those. But I can check the RAM one for you. I mean, but it's like, it's just not. How do I say? I mean, it's not what I'm looking for. It's not giving you concept. It's like one particular thing, a RAM over a RAM, and I don't really care about the RAMs, and it's not really important in this case. I mean, I'd rather look at. Yes, here are some good ones. Especially this one with the brass bolt and the one with the bolts. That's what I'm actually heading to next. So yeah, you can go over these ones over here. Some of them are roughly the same. Yeah. Okay, so are we ready for more? Can we move on? Or should I touch on my bolt problem next week? Then obviously we'll do state energy afterwards. Have you guys had enough?
Yeah, I wouldn't mind a break, eh?
Yeah, no, we're basically done for students.
Definitely, yes.
Yeah, no, I mean, I don't want to overload with information. I don't feel that it's fair, but to know, can you guys still take another concept? Because I mean, this is like a whole new concept. This chapter basically finished. Yes, Mr. Oh, I know he dropped his hand. I don't want to push. Yes, Sasha, go for it.
Just what I found helped quite a bit with this chapter, because the calculations, it's quite time consuming, especially if you're using the Casio to save the areas as values as A or B in your calculator, and then just refer to them as the letter later on, especially when you're doing the calculations, because when you have to keep doing the area every time, it becomes quite time consuming.
Fantastic. Guys, is it tough for you? Yeah, I mean, I'll just use matrices. I have my own ways of doing it. So there you go. Okay, guys, I think what I'm going to do now, I'm going to make sure you cover this. I'll post the slides up, but once we get back next week, we're gonna finish. Tempest is essentially finished now. But what I really want you guys to actually do, in preparation for that, and obviously I explain it, and this is where it's the key problem. You know, this is the one I really wanna touch on. Let me just quickly share it with you guys. I'll share the slides once I'm done now. Well, not now, but I mean obviously a bit later. We've essentially covered everything. And yeah, this is the one. So I think this is similar to what do you guys have here? It's 7.6, but yeah, 7.6 doesn't account for an extra loading. So like who does it? Rigid washers. Yeah. So we're gonna touch on this problem next week. I think it'll be a good start to touch on this. Sustained energy is not a particularly difficult or big chapter. How many pages is it? It's like what? Let me have a look here. It's like 123. Yeah, it's like literally 9 or 10 to 11 pages. Certain parts we don't touch. So in that tutorial, I put up push and pull problem, and we will get back. I'll solve this one with you guys, and obviously you guys have to solve that one, and then yeah, it's worth focusing on. Yeah. Okay, guys. Thanks. So next week we'll just continue with that example. Then we go on to strain energy, which we'll probably complete as well. It's not as difficult as it's really a plug and play. Just gotta know how to use the formulas in the next chapter. Yeah. Okay. So anyway, guys, thank you for attending, and see you next week Monday. And guys, don't forget to test. Your test is on the on the Monday the 30th.
What
So,
time are you going
thank
to
you.
do electros?
So did I have an announcement already? Yeah, it's not on here.
Sir,
Yeah. Yes, go for it.
yeah, can you share the link for Electros on
Yeah,
WhatsApp if
I
it's
didn't.
possible?
I thought I've sent it already, man. Like I kind of I really set it up, so that's why I'm like, it's not that time yet. Okay. But anyway, we'll start at we need a bit of a break. So let's start like 12:30. So we're starting with decent machines. It's not that heavy. The start anyway, and then yeah. So it's gonna come out soon, and then we can just start at 12:30. I think it's a decent amount of break. You know, obviously we have a session on Wednesday which you can continue. So yeah, okay guys, see you for electros then. Some of you guys have NAVOC as well. Okay then guys, cheers, see you. And please be cognizant of the test. So yeah, if you want to prepare, start preparing immediately.